Before we start, please, we need your help to keep growing. Please consider subscribing to our channel. Now, this is going to blow your mind. Seriously. We're living through the biggest shift in software development since, I don't even know when, and almost nobody is talking about it. I just read an article from Wilson Lin at Cursor, the company that's basically become synonymous with AI-powered coding, and what they've discovered is absolutely groundbreaking. The article is called Scaling Autonomous Coding, What We Learned Running Hundreds of Agents, and it's not hype. It's not marketing. It's an engineering deep dive into something that should frankly terrify and excite you in equal measure. They've figured out how to run hundreds of AI coding agents simultaneously on a single project. Not sequentially, not taking turns, hundreds, at the same time, writing over 1 million lines of production code in a week. Think about that for a second. What used to be a 6-month engineering roadmap for a team of 50 engineers, now it's a week. A single week. So, follow along with me as Wilson breaks down exactly how they did it, what went wrong, what they learned, and what it means for all of us. This might fundamentally change how you think about your career in software. Let's dive in. We've been experimenting with running coding agents autonomously for weeks. Our goal is to understand how far we can push the frontier of agentic coding for projects that typically take human teams months to complete. This post describes what we've learned from running hundreds of concurrent agents on a single project, coordinating their work, and watching them write over 1 million lines of code and trillions of tokens. And here's what this means for the future of software development. We're watching the commoditization of complex engineering work happen in real time. What used to require months of coordinated human effort, design, architecture, implementation, testing, can now be distributed across hundreds of AI agents working simultaneously. That's profound. For indie developers and small teams, this is liberation. For enterprises, it's a capability shift that fundamentally changes what's possible. The limits of a single agent. Today's agents work well for focused tasks, but are slow for complex projects. The natural next step is to run multiple agents in parallel, but figuring out how to coordinate them is challenging. Our first instinct was that planning ahead would be too rigid. The path through a large project is ambiguous, and the right division of work isn't obvious at the start. We began with dynamic coordination, where agents decide what to do based on what others are currently doing. Think about what this reveals about AI reasoning. These aren't pre-programmed workflows. Agents are deciding what to do based on real-time context. That's closer to how human teams work than traditional software ever was. But here's where it gets interesting. The humans at Cursor discovered that unrestricted agent autonomy creates problems. Too much freedom leads to chaos, just like it would with human teams. Learning to coordinate, the hard way. Our initial approach gave agents equal status and let them self-coordinate through a shared file. Each agent would check what others were doing, claim a task, and update its status. To prevent 2 agents from grabbing the same task, we used a locking mechanism. This failed. In interesting ways, agents would hold locks for too long or forget to release them entirely. Even when locking worked correctly, it became a bottleneck. 20 agents would slow down to the effective throughput of 2 or 3, with most time spent waiting. The system was brittle. Agents could fail while holding locks, try to acquire locks they already held, or update the coordination file without acquiring the lock at all. We tried replacing locks with optimistic concurrency control. Agents could read state freely, but writes would fail if the state had changed since they last read it. This was simpler and more robust, but there were still deeper problems. With no hierarchy, agents became risk-averse. They avoided difficult tasks and made small, safe changes instead. No agent took responsibility for hard problems or end-to-end implementation. This led to work churning for long periods of time without progress. This is fascinating because it mirrors real organizational dysfunction. When there's no clear authority or accountability, people, or in this case AI, default to risk-averse behavior. It's the same pattern we see in flat organizations without clear decision-making structures. The Cursor team had to learn what thousands of years of organizational design already knew. You need some hierarchy. Pure consensus doesn't scale.
Planners and workers.
Our next approach was to separate roles. Instead of a flat structure where every agent does everything, we created a pipeline with distinct responsibilities. Planners continuously explore the codebase and create tasks. They can spawn subplanners for specific areas, making planning itself parallel and recursive. Workers pick up tasks and focus entirely on completing them. They don't coordinate with other workers or worry about the big picture. They just grind on their assigned task until it's done, then push their changes. At the end of each cycle, a judge agent determined whether to continue, then the next iteration would start fresh. This solved most of our coordination problems and let us scale to very large projects without any single agent getting tunnel vision. And this is where it gets powerful. By introducing structure, planners, workers, judges, the system became dramatically more effective. This isn't revolutionary management theory. This is basically how Google organizes large-scale software development. But here's what's new. They've automated away the human middle management. Planner agents are doing what senior engineers do. Worker agents are doing implementation. Judge agents do code review. A 3-person startup can now deploy an organizational structure that rivals a Fortune 500 company's engineering division. Running for weeks. To test this system, we pointed it at an ambitious goal: building a web browser from scratch. The agents ran for close to a week, writing over 1 million lines of code across 1,000 files. You can explore the source code on GitHub. Despite the codebase size, new agents can still understand it and make meaningful progress. Hundreds of workers run concurrently, pushing to the same branch with minimal conflicts. While it might seem like a simple screenshot, building a browser from scratch is extremely difficult. Another experiment was doing an in-place migration of Solid to React in the Cursor codebase. It took over 3 weeks, with plus 266,000 minus 193,000 edits. As we've started to test the changes, we do believe it's possible to merge this change. Another experiment was to improve an upcoming product. A long-running agent made video rendering 25 times faster with an efficient Rust version. It also added support to zoom and pan smoothly with natural spring transitions and motion blurs following the cursor. This code was merged and will be in production soon. We have a few other interesting examples still running. Java LSP, 7.4K commits, 550K LOC. Windows 7 emulator, 14.6K commits, 1.2 M LOC. Excel, 12K commits, 1.6 million lines of code. Let that sink in. Millions of lines of production code, a working browser, a React migration that took weeks at Google scale scope, all written by AI without a single human touching the keyboard. This isn't a proof of concept anymore. This is production reality. And these aren't even the only examples. There are 3 others still running. The implications are staggering. What happens to junior developer roles when this technology becomes commodity? What happens to outsourced development when any company can spin up 500 agents? What we've actually learned. We've deployed billions of tokens across these agents toward a single goal. The system isn't perfectly efficient, but it's far more effective than we expected. Model choice matters for extremely long-running tasks. We found that GPT 5.2 models are much better at extended autonomous work, following instructions, keeping focus, avoiding drift, and implementing things precisely and completely. Opus 4.5 tends to stop earlier and take shortcuts when convenient, yielding back control quickly. We also found that different models excel at different roles. GPT 5.2 is a better planner than GPT 5.1-Codex, even though the latter is trained specifically for coding. We now use the model best suited for each role rather than one universal model. Many of our improvements came from removing complexity rather than adding it. We initially built an integrator role for quality control and conflict resolution, but found it created more bottlenecks than it solved. Workers were already capable of handling conflicts themselves. The best system is often simpler than you'd expect. We initially tried to model systems from distributed computing and organizational design. However, not all of them work for agents. The right amount of structure is somewhere in the middle. Too little structure and agents conflict, duplicate work, and drift. Too much structure creates fragility. A surprising amount of the system's behavior comes down to how we prompt the agents. Getting them to coordinate well, avoid pathological behaviors,
and maintain focus over long periods required extensive experimentation. The harness and models matter, but the prompts matter more.
Here's the critical insight. Prompts matter more than the underlying model. This tells you everything about the future of software development. It's not just about having powerful models, it's about knowing how to instruct them. This is where the real skill gap opens up. Any developer can use Claude or GPT-5, but the developers who understand how to prompt, structure, and guide multi-agent systems, those are the ones building the future. This is the new competitive advantage. What's next? Multi-agent coordination remains a hard problem. Our current system works, but we're nowhere near optimal. Planners should wake up when their tasks complete to plan the next step. Agents occasionally run for far too long. We still need periodic fresh starts to combat drift and tunnel vision. But the core question, can we scale autonomous coding by throwing more agents at a problem, has a more optimistic answer than we expected. Hundreds of agents can work together on a single codebase for weeks, making real progress on ambitious projects. The techniques we're developing here will eventually inform Cursor's agent capabilities. If you're interested in working on the hardest problems in AI-assisted software development, we'd love to hear from you at hiring@cursor.com. And here's what I think is crucial. As this technology evolves, we need platforms that celebrate and showcase what's being built. We need communities where developers share their vibe-coded creations, where AI-assisted projects get the recognition they deserve. That's exactly what Vibe Codev is building. It's a discovery platform for apps built with tools like Cursor, Claude Code, and other AI development tools. It's where your agentic coding projects get discovered, voted on, and celebrated by a community that gets what you're doing. If you're building with these tools, if you're exploring the frontier of AI-assisted development, Vibe Codev is where your work belongs. Check it out at vibecodev.com.